Put the recording on and share the screen here. Let's start with this. So just a very quick recap what we did yesterday. Basically, this was the main issue yesterday, the simplex algorithm. So here, choosing a feasible basis, then doing the simplex algorithm, not going to go step by step here, but we talked about the optimality, and there are two possible outcomes, like I said. Either you find out that the problem doesn't have a bounded solution, or you find out that it has a solution and you find it. But it's all contingent on finding a feasible basis. And if you don't have a feasible basis to start with, then there were these two modifications that we discussed, either the big M method or the two-phase method, both of which are based on the idea that you introduce new variables that guarantee that you can find a sub problem or an extended problem that definitely has a easy to find a feasible basic solution. And then after you've done that, you kind of solve this new problem either to get a solution to the original problem, or you solve it to find a basis for the original problem. Either way, the attempt to solve this modified or this extended problem will then reveal to you whether the original problem has a basic solution. Okay, there were examples which I'm going to skip now. I noticed that we're actually progressing a little bit slow on this course because this online teaching seems to be a bit slower than classroom teaching. So duality. So the duality is a concept in a lot of mathematics. So it's not just here, but you will encounter the concept of duality, the dual of something. There are, in linear operator theory, there are duals of certain kind of spaces. Very often the case is when you have some concept or some model, then it has what is known as a dual. And in the dual, you can often do something more easily by an operation that is hard to do in the original. So I'm not sure, sorry, the dog is in my feet. So where was I? So yeah, so for example, the Laplace transform can be thought of as, in some ways, it's not really, but you can think of a Laplace transform as a duality, or the Fourier transform as a duality. So there's an alternative representation for the same thing. And then some things are easy to do in that transformed version, and then do the transformation backwards, it corresponds to something else. This kind of phenomena appear virtually everywhere in mathematics. And this is one place where they appear. So the concept of a dual of a problem. Here we have a minimization problem with a certain cost vector. So let's call this C transpose. It's a cost vector. So it has for each of the variables, it has issues a cost. And then we have these linear constraints. It's matrix A times X, and that should be equal to B. So we have the right-hand side of those constraints. So a certain linear transformation of your solution has to result in B. So it's constrained there to be equal to B, AX, while C transpose X gives you what the cost is. And now the cost is to be minimized. And the dual, on the other hand, is a different problem, one where you're maximizing a U. Now you have a U, which is a new variable, some different variable, and you're maximizing basically B transpose U, and you have a constraint which says that A transpose U must be smaller than or equal to C. So let's not go deep into any interpretations of this, but it's like the constraints and the costs have exchanged places, and minimization has become maximization. And the equality is then corresponds to an inequality. And certain questions about the linear programming problem, the original standard format problem, can be answered easily using properties of the dual. So there is a correspondence between these two problems. And the reason for using the dual may be that there are situations which may be hard to detect. For example, just give a simple example is, we noticed in the simplex algorithm that sometimes if we solve for the linear programming problem, then the problem doesn't have a solution in the sense that it's unconstrained. It can, you can find a direction in which to move X indefinitely and the cost will simply go down. And if this is so, if this is so, then really what this amounts to is that the dual, on the other hand, will reveal this more readily. So because, it may happen that you run the simplex algorithm for very long until you find evidence that, oh, this is unconstrained. On the other hand, there is a duality in that the dual problem, on the other hand, may be unconstrained or unbounded as well, and it may increase indefinitely. And that situation means that in this situation, the original problem, in fact, doesn't have any solution. We'll see that this is so. Let's just first look at what the dual looks like. Here's an example. So I'm going to skip this. There is this definition 3.15. We can derive from this 3.15, and there is also a possible way for a general linear program or a linear program that is not in standard format to be constructed as a dual. And here's another way, is that if the original problem is a maximization problem, then it becomes a minimization and vice versa. If the original problem has a constraint, then for each constraint, we introduce a variable in the dual. And if that constraint is an inequality constraint, we introduce a variable that is bounded from either below or above, depending on whether the constraint is upper limit or lower limit. On the other hand, if there's a constraint that posits equality, then we can introduce a free variable. And similarly for variables that are positive or negative, we can find constraints. But I would just, for this, to make the scope of this problems more, or this material a little bit more constrained, let's just say that this is a curiosity. We will always deal with the standard format problem, and the standard format problem has a very easily and readily made dual in which we are maximizing this B transpose U subject to A transpose U is smaller than or equal to C, and this U is a free vector in the sense that it can be positive or negative. And the original, we assume that it's in standard format. So it's a minimization of a linear function subject to a linear equality condition, all variables being positive. All right, let's move on. So here is we won't go to these examples because these examples cover this table 3.1 problems all, but let's see. Let's go here. So the dual of the dual, it becomes the original. So very often we call the original problem the primal, meaning it's the first problem, and the dual is the secondary problem. And the dual of the primal is the, sorry, dual of the dual is the primal. We could when we use these constraints, but that's not important. We don't need to discuss that part now. Really, what is the important thing here is that let's say that we have a linear problem, linear programming problem, and let's assume that it's in standard format. And we construct a dual so that instead of minimizing C transpose X, we're maximizing B transpose U. And the important part of this theorem says that the dual, whenever we have something that satisfies the U, that satisfies the dual here, that A transpose U is smaller than or equal to C, the equality holds that the cost function at that point, no matter what it is, if it satisfies the constraints, it's less than anything that any cost of the original linear problem. And that if it just so happens that we find a U such that B transpose U is equal to C transpose X for some X and U, then both X is now a solution to the original LP problem, the primal, and U will now be a solution to the dual problem. These two true properties give us a very good way of gauging, faster, what kind of solutions the linear problem has. Instead of just running the simplex algorithm, we can come up with ways of analyzing it more readily. Let's look at this proof first. Firstly, this is fairly simple because in the dual problem, A transpose U must be smaller than or equal to C. Then we can take the transpose of that. So we get U transpose A is smaller than or equal to C transpose. Now if we take X, remember that AX equals B. If X is a solution to the original one, then it follows that U transpose AX is smaller than or equal to C transpose X, following the first law, which is multiplying this with X. And then we get that U transpose B must be smaller than or equal to C transpose X. So whenever U is satisfies the constraints of the dual, and XX satisfies the constraints of the primal, then it's true that B transpose U is smaller than or equal to C transpose X. Now, on the other hand, if we have feasible solutions such that C transpose X is B transpose U, then obviously all the solutions of the primal must be larger than or equal to this, because we know that B transpose U is always smaller than C transpose X for any X. And similarly the other way around. So what we really have in the primal and the dual is that the solutions of in terms of cost of the primal are always, there's let's say that the minimum is here, then the dual has solutions like this, and they meet at one point or maybe several points, but if they meet at several points, the value is always the same, and they have equal, the cost is equal for both the maximum of the dual and the minimum of the primal. And this is really a fascinating thing, because really what we're doing to this obtain this dual, we're just transposing the matrix A, replacing X with U, and just changing the roles of B and C, and then getting a new vector and optimizing. Now we're maximizing this U instead of minimizing the X. And then we have this. Now, what can we build from this? Well, let's first look at this theory a little bit further. So we define this so-called simplex multipliers. And these simplex multipliers, when we have a basic solution and we have a basis for the linear problem, then we can define the simplex multipliers for this as simply the cost vectors B part times the inverse of the basis. It will soon become apparent why we do this. It will soon become apparent why we do this. Now, assume that we have a optimal basic solution for the linear problem. Then we have the situation that the simplex multipliers will then be an optimal solution for the dual. So we have that C transpose, if X star is an optimal basic solution, then C transpose X star will be equal to B transpose this pi star, where pi are those simplex multipliers. And this follows from the previous theorem, which posits the optimality of the linear problem. So just not very, so if you look at the reduced costs, which we assume that at that given that basis are positive, right, or non-negative, and then we replace this part. This part here, the CB transpose B inverse appears in this. So we could replace this by what we know that this is in fact what is known as the simplex multiplier. And then if we look at the other part of that, then this part where we have the CB transpose minus CB transpose B inverse B, so this is simply zero because there's B inverse times B here. That's identity matrix times C transpose. So this is a zero vector, and this is C transpose B minus then the simplex multipliers times B. And we can look at this C then here. It's A transpose this pi star then. So this pi star is now a feasible solution. It's feasible, meaning that it's exactly equal to C. They have to be smaller than or equal to C, but to satisfy the dual constraints. It's feasible there. And because in the optimal solution, X star n, that's the null part. It's by definition, it's zero because it was a basic solution. Then we have that this B transpose pi star is in fact C transpose X star. So what can we do then? Well, the thing is, what can we use this for? The thing is, happens is that we can look at the primal, we can look at the dual and decide whichever is easier to solve, we can solve that and get the solution. The primal is very easily obtained by simply taking the dual is obtained by simply taking a transpose of the matrix and then switching the roles of B and C, right? So there's nothing, there is no computation even needed in calculating this dual. And then we can just compare these two problems. If we can immediately see, for instance, that the dual has a solution over there, then we can transform it into the solution of the primal and vice versa. And here, we don't really need to go to this corollary 3.22 because it's really, it comes without any additional thinking. Because if we have the feasible solutions for both this linear problem and dual problem, then they are actually optimal exactly when their associated costs are equal, right? So it doesn't really matter which we solve. If we solve one, we have the solution to the other. And that comes, this comes to theorem 3.23. So if these linear problems and its linear problem and its dual, if they both have feasible solutions, then they both have a finite optimal solution and the optimal values are the same. The thing is, if the linear problem, the primal problem, has a feasible solution but doesn't have an optimum, then the corresponding dual has no solutions. Why is this? Well, it's fairly easy to see. We already proved that the dual, any solution to the dual has a cost function that is smaller than a cost function to the of the primal. And if the primal doesn't have an optimum, it means that the primal has smaller and smaller values of the cost function. So you can make it as small as you want. I mean, it all goes all the way to minus infinity. It means that the dual problem cannot have any solutions, because no matter what solution you might say that this is a solution to the dual, then the primal would have a solution that is lower than this or smaller cost than this, but this is impossible because all the solutions of the dual are smaller than or equal to all the solutions of the primal. So if the primal is unbounded, then the dual is empty. This is actually what we can use quite easily. So we just look at the dual and we calculate and notice that this doesn't have a solution, that this doesn't have any solutions, simple linear algebra, and conclude that the primal is unbounded. And also the theorem 3.24, you don't have to remember this part, the so-called complementary slackness theorem. It simply says that if we have two feasible solutions, X and U, of the primal and the dual respectively, then they are optimal if and only if X transpose C minus, well, basically X transpose C, that's the cost part. And then if you calculate X transpose A transpose U, well, X transpose A transpose is simply B transpose U. So that means B transpose U. If that's zero, that it means that, you know, the solutions are the same. So it tells us something that if a corresponding variable xi, now this is just one variable, if the corresponding variable is a null variable, then or if the corresponding A transpose U I, meaning the corresponding a dual constraint is at the limit. Remember, the dual's constraints are inequality constraints. So the row of A transpose U, you know, it is smaller than or equal to Ci, right? So if that corresponding row is at the limit, so that row is equal to Ci, then we say that this constraint is binding. So at the optimum, either xi is 0 or the corresponding dual constraint is binding. It's at the limit. I'm not going to go here. Here are some examples of problems and talking about the simplex multipliers. Really, I mean, we're going to skip most of this because I think the only thing that you really need to take away from this is the idea that this dual that we define like this has this theorem 3.19, and pretty much everything follows from this. We go to the dual simplex algorithm next. I'll just explain. It comes from here. I'm not going to skip this theorem. So here, the detailed justification of this algorithm is left as an exercise, but the idea here is this. We find a feasible basis for the dual, and we solve this b xb equals b, right? So it's a it's a feasible basis for the original one, and it's feasible for the dual. And then what we do is we check, similar to simplex algorithm, we check these conditions and the reduced costs and so forth. But the thing is, if we notice that we would be going to this unbounded situation, the problem, if we could make the dual go unbounded upwards, then the original is infeasible, right? because if the dual has a larger and larger numbers, then obviously if it goes all the way to plus infinity and the primal has solutions that are only smaller than that, then the primal has no solutions. So it's basically we are looking at this in reverse. And that's the thing. So really what I want you to remember for this and take away from this is this theorem 3.19. Really, that's the important part here in duality, because the dual gives us that the cost in the dual is always a lower bound for any cost in the primal, and everything else that is important in this theory follows from that. You can browse through this, but I'm not going to ask you to do this all that much. Then there's the sensitivity analysis about the simplex multipliers and so forth, but I'm going to skip that, and also skip that interior point methods, because the main mathematics of this sensitivity analysis, the idea of the sensitivity, I just mentioned what it means. What it means is that we can use these simplex multipliers to look at how the problem's solution would react if we take the constraints in the B vector and we change those constraints a little bit. We increase or decrease them. The simplex multipliers will tell us how the problem will react. I mean, we can take the partial derivatives and then we can come up with the marginal costs. I mean, things like, just let's skip the mathematics for now. You can study it if this is important to you, if you're going to be studying if you're going to be working on a linear programming problem. Then let's say that we have a situation where we have framed some process of the industry as a linear programming problem. And we have these constraints, for instance, that we have to produce certain things, and then the variables are the raw materials, and then each raw material has a cost, and then the process is, you know, how you can produce your output product is constrained. You can use different different raw materials or different parts in different ratios, but it's constrained by this linear problem. And now let's say that you are able to change this constraints a little bit. Maybe tweak the process in such a way that some of these constraints are changed. How does that affect on, what is the effect of this on your cost? Is it worth to do this? You know, how does the cost change? So this is the sensitivity analysis. It means that, you know, it makes no sense to tweak a certain component of the process, make it somehow more efficient so that the constraint is relaxed or something like this, if it doesn't have any effect on the cost. It's not cost effective to optimize something if the cost of the end product is not changed, right? Or if the cost of the end product goes down by just a little bit and you have to spend a lot of time and energy or money to make the process better. So the simplex multipliers are sometimes called shadow prices and marginal costs. They correspond to the marginal costs of the marginal effect of changing a constraint B. Then it corresponds to a partial derivative of the cost in this basic solution sorry, if you take ZB, that's the current cost with this basis. The simplex multiplier is then the derivative of that with respect to that component of the constraint vector. So the B vector in the constraint. So if you change that a little bit, then the cost react by this marginal cost. So you get the idea. So this is sensitivity of changes in B, but then there's a sensitivity to changes in the cost function. Obviously, if you are able to lower the cost of some raw material or lower the cost of some part of that, Then there would be one that is missing is what about the sensitivity to changes in the coefficients in the matrix A? That's missing here, and that's a whole different thing, one that we didn't, that this material doesn't cover. But you know, the point of this chapter is to introduce you to the idea that after you've formulated optimization model, in this case a linear optimization model, then changes in the parameters of the model will result in changes on the cost, or the, you know, the thing that you are minimizing. What the solution looks like is, of course, you know, it's a function of those variables or those parameters, and sensitivity analysis is basically the study of what happens to the solution when you change the parameters of the system. So this is an example of that. Not going to go in depth here, just wanted to explain what this is about. All right, now let's have a small workshop here. Let's do it in this way. We have example. Okay, these examples are not very nice there. Let's see. Okay. Here is example 3.25. We have the problem from example 3.12, which we already looked at. So we have this constraints given here. They were given by introducing these slack variables x3 and x4. These are all positives, so there's a matrix there. And it has this optimal solution and then the simplex multipliers and so forth. So let's, you have the code, basically you should have the code for the exercise, sorry, the example 3.12, doing that in the simplex algorithm. In your group, go through that code that has the example 3.12. Do the part where you initialize the matrices in your group, and then look at this exercise here and verify, where was it? Verify that, what happened here? This is now jumping, sorry, I jumped. Verify this example 3.25 and calculate the simplex multipliers by use of that. All right? So just recreate these things and verify the simplex multipliers and discuss how do you get the dual of this in MATLAB. You know, how do you express, well, of course, you know how to express them, but discuss this issue and go through that, use that code, initialize those matrices and calculate these simplex multipliers there. And I'm going to give you about 10 minutes. It shouldn't take too long. And I'm going to pause the rest, something of an example that you were able to follow, at least calculate that and see that this is these simplex multipliers can be calculated in this way using the corresponding vectors. Did you manage to do that in room 1?
We have run out the time, but we.
I mentioned this just, that there are other methods, the so-called interior point methods. Those are based on the idea that you are taking a dual and you add some slack variables to the dual, and then you can use this idea to start what is called the interior point that is inside the dual space and so forth, and look for a certain multiplier, let it approach 0, and you will find the solution. I'm not going to go in here how this algorithm works, but it's possible topic for exercise if you want to discuss this. If linear problems are your cup of tea, so to speak. We discussed these problems already and have plenty of examples here. We'll skip that now and move on to the next theoretical problem topic, which is the unconstrained optimization. So this is a very, the nature of the linear programming problem is peculiar to, or particular to, the linear problems. It does have this idea, similar, like someone mentioned in our warm-up, that it reminds us of the gradient methods. It does, it really does. The thing is, we are looking at the direction. The simplex algorithm is based on the idea that we are looking at the direction, a single variable that we can increase to make the cost function smaller. In general, in unconstrained optimization, we don't have necessarily these linear constraints, so we have to deal with something else. We can use, there are ways of dealing with nonlinear constraints. We talk about that later, but first let's look at the situation where the cost function itself is nonlinear. So you're probably familiar with some very common or simple problems in this unconstrained optimization, this genre, if you will. For instance, finding the optimum of the minimum of some polynomial, let's say 2 times x squared plus x. Well, you can find the bottom of the parabola and so forth. So that's fairly easy. But in general, these problems are in Rn, you know, in a very large space, multi-dimensional space. The function can be very complicated. Let's first look at this. What we call this problem a free problem, in the sense that we can pick any point in our space, Rn, and we are in any of those points in Rn. We can then say that, okay, the function value in this point, we can calculate it, and if it's good, then we could take it, right? We're looking for the minimum, so obviously we will not be satisfied unless, sorry, unless we're pretty confident that it's the minimum. Sorry, I have a little bit of dryness in my vocal cords. So if we don't have to worry about any constraints, then we can just move around in the space until such a time as we find the minimum. Very often the problem is, of course, that if you think, I mean, it's probably easiest to think in terms of 2 dimensions at least, so that you have this landscape and you're looking for the lowest point in the landscape. It's not easy to find it if you just calculate the value of the function in certain points. Often, in fact, we can't find the global minimum, even if it exists. So we'll have to settle for a local minimum. Local minimum, it means that, you know, there's this point around which, let me just grab a pen and paper. Sorry about that. I switched tables just the other. So we have a point here. Here's our space. Right? That's a point, right? You see the point there. So a local optimum means that there is some region around this point, an open set like this, so that that point has the smallest value as long as we are inside this open set here. That's what it means to be a local minimum. And this happens when we have a function that, I'll draw an example. Let's say we have a function that behaves like this. This is the graph of a function. This is one dimensional. So we have here a local optimum because there is a region here between this and this number here that bottom of this bit is the smallest, but it's not a global minimum because this is a global minimum. And most of the methods that we deal with in this chapter are geared towards finding a local minimum. And that's a problem. If we don't find the local minimum, if we find the local minimum, there is often no way to verify that it is not the global, or whether it's a global minimum. So here's a structure of what we call iterative methods. Most of the methods we will talk about here are iterative methods. Like someone already said, so is the simplex algorithm. The simplex algorithm was an example of an iterative method. And all the iterative methods work as follows. We find an initial point, x0. Correspondingly, think about the simplex method. We found the initial basis and we solved for the xb. When we are at the current point, we find a direction to which we go. In the simplex method, this was basically finding the null variable which we increase, and then we can just analytically solve how far we can go there, and we just move there. Moving from one, basically, if you think about it, it's not, like I said, it's not completely accurate description of, but if we think about the simplex methods constraints set as forming a polygon, a multidimensional polygon or a polytope, we're moving from one corner to the next corner. And when we're at that corner, we look at it again. We iteratively move until, well, we basically move until we find the one that correspondingly has the lowest cost. So it's a descent direction, meaning we find a place where we know we go in that direction, we make the function smaller. Often also we have to determine this so-called step length, that is tk. And in the simplex method, really we could analytically solve this by looking at, you know, how far do we go in that direction? How much can we increase that particular value, so we know which of the basic variables that we still have non-zero becomes 0 first, and then we switch those, and we're actually traveling in that direction along that axis. And now this variation in what kind of algorithms we will be dealing with. There are variations in all of these points in which what we do. So basically, what direction do we go to? That's a matter of the algorithm. How far do we go in that direction? That also is determined by the algorithm. And the fifth part, how long do we go about doing this? When do we stop? So there are situations, there are various reasons to stop. One, you know, it's 3:30 p.m. and the boss wants to get the best possible result by 4 p.m. So we have to stop the algorithm at 3:30 in order for us to put those numbers in our report and say, this is the best point we could find. And I'm not joking with this. This is an actual thing that happens, that sometimes you run an optimization algorithm for as long as you have time, and then you have to stop because you don't have no more time. It could be that you are satisfied when you find a local minimum, so that if you're using gradient-based methods where you calculate the gradient of the function, then the gradient is very, very small. If the gradient is very small, it's not worth traveling anywhere. You're very close to the optimum if it's very small. So the thing about this is that using the algorithm, and this of course depends on what the problem looks like and what the method is, but using the algorithm makes sense only if we can prove that the sequence of points, you know, the current point xk, the next point xk plus 1, xk plus 2, and so forth. The sequence of xk points converges to the solution of the problem. And by the solution, we mean the sort of solution we can contend with. It may not be, like I said, it may not be the global optimum, but at least it's the sort of point that we look for. And this is very often the situation that we cannot really hope to prove, other than, okay, it would converge if we did infinitely many of these, but really we have to settle for a finite number of steps. Obviously, you have to settle for a finite number of steps because, as far as I know, we don't have computers that can run infinitely many steps all at once. We will usually skip all those proofs that prove convergence. Instead, we will resort to saying that something very generic, that because this is, let's say that because this is a convex problem, this is a convex function, we can find the minimum, or something like this. We can alternatively prove something about that, but not necessarily full convergence. So let's look at some of the algorithms that we can deal with. There are several ones that we must look at, and then there are things to consider. How long does it take to calculate the next iterate? What do we know about the function that we can use? I mean, very often it is the case that the function we're dealing with, we can't, for instance, calculate the gradient because it doesn't have one. Let's now have a small 5-minute discussion where you think, each of you, I mean, this is just for you guys to think in the group, but I'm just going to recreate this, and instead we'll have just 2 rooms, 5 participants in each room. And what I want you is, each of you guys to do is to think of a problem that you think is an unconstrained problem that you have encountered, one that you might think would be solvable using this method. If you can think of anything. If you can't think of anything, just think of a function that people sometimes minimize, that you can calculate the gradient, or if you can't calculate the gradient, think of that. Just try to think of examples of optimization problems that might fit this template, or if not, then mention, oh, it doesn't fit the template because of this. And let's just use 5 minutes on this, right? Just discuss among each other this. What do you think? Can you spot this template in your previous experience? Let's resume now. And so let's look at this things. So there are various things that we have to figure out. Finding the step length, finding the direction, and so forth. So let's first look at finding the step length. And in finding the step length, we are kind of moving from the point xk, and we have, let's say that we've determined the direction dk. So let's just go back here. The dk is the direction, tk is the step length, and xk is the current point. And let's assume that we have already know where we are going, dk, that's the direction. And we are at xk, obviously we know where we are. And then the thing to determine, number 3, finding the step length, you know, is how far should we go in that direction? And that means that we transform this minimization of a possibly vector valued problem into a problem of one variable. So there's just now, we already know the direction. It's only about the magnitude of how far to go in that direction. So there are methods that we can do here. Obviously, if it's differentiable, if the function is differentiable, then we can find basically what is known as the directional derivative, or the Getto derivative, which we mentioned, and then just, you know, sorry, forget. So that was about the direction. Do not listen to me on that. So we know which direction we are going. So we are taking the derivative of f, and we're moving to t times dk. So we know already that the directional derivative in that direction is the dk times the gradient, basically. The dot product of the gradient and the direction. That's the directional derivative. And then, you know, if we look at where we are going, xk time plus t times dk, we calculate the derivative of that with respect to t. And that's basically the difference quotient that you can find in the Gatto derivative region times dk, and we find out that whenever this dot product here goes to 0, then that's how far we go. And I think this is visually represented easiest. Let's say that we've picked the direction where, no, it's really hard because you're looking at this video. I mean, I usually do this in classroom with a pointer, so you see that I'm twisting it, but there's no 3D here. So let's say that we are going in this direction. We are at this point at the end of this pen, and we're moving in along this line in this direction. Now, the gradient may point in some direction. I don't know if it points exactly in that direction, but it points somewhere. And really what we are looking at here is the gradient at that point and its dot product at dk. So let's say that this is the gradient points in that direction, but when we start moving, the gradient points in different direction. And at that point, when we get there, it's perpendicular to this direction we are moving on. And at that point, that dot product is 0. So this is as far as we go. That's my step length now. If we do this gradient, this derivative-based method. Well, the problem is that more often than not, we cannot do this analytically. We can't just solve for the 0 of the gradient and go there. So very often we have to use numerical methods. So we try different values of this step length, t. And sometimes we can, of course, solve it analytically, but we can do it in very different ways. One, we increase it, we calculate, you know, very densely, we calculate these points until such a time as the cost function starts increasing again. So we go to the last point where it no longer decreases when we go in that direction. On the other hand, it could be that we can analytically solve it and find a global minimum. I mean, maybe it goes down, up, until such a time as there's a low global minimum. So we go as far as in that direction as we possibly can. If it's a global minimum we find, then yeah, we obviously want to go as far as we can. And the third strategy is to find any minimum. Well, in fact, it says minimum, but we can just go to basically any point as long as the function obtains a value that is smaller than when we are currently. Because, you know, if we want to look for a point that is better than now, then any point in that direction that has the cost function smaller than where we are now is an improvement. So we can be satisfied with any improvement whatsoever. Obviously, how this affects how fast we get to the minimum or whether we get to the minimum depends on how we select the step length and, of course, what the problem is. So we cannot really guarantee that even numerical method find a nice solution for even a local minimum or a global minimum, because if the derivative is fickle in the sense that we probably cannot find exact step length that takes us to a 0 of the derivative of this univariate problem. On the other hand, sometimes when we talk about these algorithms, we assume that we are picking either the local minimums or global minimums. So be wary of a situation where you have said that, oh, this algorithm works very well and it optimizes the problem if these conditions are not met. What are the assumptions? So if you're going to be reading at some point, some of you may be reading the literature for finding a optimization algorithm, and then the optimization algorithm has been proven to converge to the optimum. But then maybe the assumption is that, you know, the step length is determined by a global minimum. But in reality, you are only looking for some kind of minimum. Then obviously the algorithm doesn't necessarily converge, even though there is a proof that it converges, but because you're actually doing something differently than what is assumed in the proof. There are problems, and this goes to those people who work in machine learning, for instance. This is the thing, if the step length is too large, the algorithm might oscillate. I don't know how many of you, if any of you work in machine learning and things like neural networks or something where you kind of do usually you do some kind of error minimization. So there's a classification error or an output error of a neural network or some kind of other system, parameterized system. It produces an output, and you are trying to teach the system to produce the correct output. So you know, if it's supervised learning, you know what the correct output is. So you know, maybe you calculate the derivatives, like in backpropagation method, you calculate partial derivatives of the networks, these coefficients, and then, you know, the step length or the learning rate. If it's too high, then you overfit. You adjust too much to the direction of the latest input, and then, you know, even if you try to teach it with similar inputs and outputs, then, you know, it may result in oscillating. It doesn't find the optimum or the minimum, even the local minimum. Instead, it just goes about, it overshoots and then undershoots, overshoots, undershoots, and so forth. You know, and you're minimizing the let's say the sum of squared classification errors. If the step length is too small, the algorithm might stop and think that, okay, we can no longer improve. We're trying too small steps, and if the step is too small, we notice that, okay, it's no longer changing. The error is no longer going down, so we stop, and then, you know, the algorithm ends prematurely. Here are certain ideas for the step length. If you are able to calculate the derivative of this step length, then you know, find a coefficient that binds the change in you know, this G is how much. This G gives you, G at 0 is where you are at. This pen again is the direction, and T is how far you go in that direction. So make sure that you go far, you don't go too far, and then the other here is find another bound that makes sure that you go far enough. Not going to go to this Goldstein's criterion. They can be found in the literature. There is another one that binds that if you have a normalized step length, which is, let's say, 1, if it's too large, then multiply it by some number that is between 0 and 1, and repeat until you found the suitable step length. So you kind of scale down the step length from where you were. So these are, you should return to these if you are going to be, I'm not expecting you guys to memorize these, there's not enough time for this, but the idea here is that there are all these tweaks you need to do on the step length if you're working. And this is especially true for those who will be working on machine learning oriented ways, where you are tweaking the parameters of the system to minimize a classification error, then the step length is a crucial thing. And these considerations work there very well. Well, not work very well, but they are very important there. Then there is the question of stopping criterion. When do we stop? When do we stop? I mean, that's an important thing. Obviously, if we find the global minimum, we stop. But how do we know? How do we know we are, if we find a place where we are close enough to the global minimum, then we might want to stop because, you know, the error is not big enough to matter. So when do we stop? One possible way is that once the algorithm runs, if we just didn't move, if we didn't move that much, if we move just a little bit, moving very little, there's a tolerance. Let's say that, again, let's say that we are content with being inside, if we know that the minimum is this dot and we are content with being this close to the optimum, then as long as we move less than some fraction of the diameter of this tolerance for the minimum, then we can stop. So if the algorithm is no longer pushing us in any direction very far, then we might stop. The other possibility is to have a criterion for stopping when the function doesn't change anymore. So if you move from one point to another, you may even move for a pretty long distance, but the function itself doesn't budge. So maybe we found a valley that is a bottom of maybe it's a multi-dimensional problem, and then there's like this valley. You know, I'll show you later an example of this kind of like a banana function. There's a banana-shaped valley, and then the bottom of the valley is somewhere in the edge of the banana. And you know, if you're moving at the very bottom of that valley, then the function no longer changes that much. Third possibility, if you can calculate the gradient, one possibility is to say that the gradients, you know, that's basically the derivative is very, very close to zero. So the norm of the gradient is so small that it doesn't really matter where we are going. We're very close to the optimum. And this is expressed in terms of tolerances, tolerance 1, tolerance 2, tolerance 3. There may be other proportionate things that we do. So we may have some other ways of doing this, but these are just examples of when do we stop. Like I said, it's not said here, but we stop when we are running out of time. Because that is more often than not, that's actually what we need to do. Is we stop when we run out of time. We'll search for better and better points, but at some point, no longer do we have the time to wait. We need a solution now, so we use the solution, the best solutions found so far. Of course, not all problems yield to this. Then sometimes we cannot just content with anything other than the best solution. But if we are content with approximation or approximative answers, then it is perfectly feasible for us to just keep on optimizing until we run out of time. I'm not going to talk about the convergence results that much. Just mention that iterative method converges to a point x star if the limit, if we were to continue this indefinitely. So basically it's the stopping criterion satisfied before infinity, obviously, that prevents us from actually doing this to infinity. But forgetting about the stopping criterion, if we were to continue the algorithm infinitely, the xk point is the one point that we have, and then we take the next point and so forth. And so if the limit of xk as k reaches infinity is x star, then we say that this algorithm converges to the point x star. So the stopping criterion basically determines how close to that point do we stop. Or it should basically determine that. It doesn't necessarily determine it, but it should. And this convergence, we say that the convergence is linear. If, you know, if you have some coefficient C such that, I mean, read this so that the next point in the iteration is closer to the optimum by a factor of C, which is less than 1. Sorry, greater than 0, and yeah, linear, well, it should be less than 1, shouldn't it? No, it should. Which way was it given? Xk plus 1 is, so the distance is smaller than C times the distance before. It should be smaller than 1, shouldn't it? Because if it's more than 1, then it doesn't actually guarantee us anything. Here, this one, linear. If C is greater than 1, it just says that the next point can be further away than the previous point, or than the current point. So probably we want this C to be smaller than 1. In any case, this is what is known as a linear convergence. So maybe, you know, every iteration shaves 10% off of the distance to the optimum. Superlinear, meaning that the points get closer and closer to one another, not just to the X star, but also closer to one another. Sorry, no. The next point is so much closer than the previous point that the if this point is 10% of the way, then the next one is less than 10% and so forth. The distance, you know, the convergence, if you think in terms of this C, there is no constant C here, but this, if you frame it in terms of this way, then the C here is a function of K, and then the C also goes towards 0 when we go closer. I mean, think about it, divide this by that, then it says this is smaller than C, but if it's smaller than CK and CK goes to 0, then we say it's superlinear. Sorry, Q superlinear. And superlinear, meaning that it's faster than linear if we are, if this convergence is faster than the norm is now taken to some power greater than 1. And quadratic means that it's the distance is less than some constant times the square of the distance. Remember that if this distance gets closer and closer to 0, then the square of the distance becomes even closer to 0. And convergence, also we say that the convergence is global if the convergence happens from any point. So these are basically the limiting factors or the differentiating factors between different algorithms. How fast do they converge? Do they converge regardless of where you start from? You know, and then the question is how the algorithms differ is how do you distinguish the step direction? You know, where are you going? The step length, and what is the stopping criteria? So we're going to stop here. Next week, we will be starting to talk about these methods for one-dimensional minimization. So it's simply minimizing a function of one variable. We start from there because this is needed in what is known as the line search. We call it line search because we have a line, the step direction, the search direction determines a line. And we're doing a line search. Basically, we're moving along this line and trying to find the best possible point. And that means that we are transforming this problem into a one-dimensional problem. So the t is now just the length, which is just a number, and we're going in that direction and minimizing this function value in that direction. And we'll look at that next week. And there are different methods of doing that. We'll talk about the gradient method and Newton method and so forth. But that's all for today. I'm going to stop the recording, and we have a